The following are absolutely needed considerations and requirements for designing and manufacturing wiring harness protective channels. Also, it is a standard requirement for all other plastic injection molded products. However, when designing and manufacturing wiring harness protective channels, a focus on safety and reliability is crucial due to the high liability and safety risks associated with electrical systems. This requires adherence to industry standards and careful consideration of materials, design, and manufacturing processes to ensure the integrity and performance of the harness. Some of the information is redundant, but it is absolutely necessary to know and use for engineering wiring harness protective channels. Do not take it lightly. When designing wiring harnesses, protective channels, or conduits, are crucial for shielding wires from environmental hazards and mechanical stress. Here's a breakdown of key design guidelines. 1. Understanding environmental factors. Temperature. Consider the maximum and minimum temperatures the harness will experience. Select materials with appropriate temperature resistance. Vibration. In high vibration environments, choose protective channels that can withstand repeated stress and prevent fatigue. Moisture and chemicals. If exposed to moisture, dirt, or chemicals, select corrosion-resistant and chemically resistant conduits. Abrasion. Areas prone to abrasion require channels with high abrasion resistance. 2. Material selection. Plastic conduits. PVC-coated metal offers liquid-tight and corrosion-resistant protection, commonly used in factory wiring. LDPE low-density polyethylene provides corrosion and chemical resistance, flexibility, and durability, suitable for telecommunication and trenching. Nylon offers excellent impact resistance and abrasion resistance, ideal for vehicle harnesses and hydraulic hoses. Polypropylene PP high flexibility, compression strength, and low temperature resistance, suitable for engine cable assemblies only if the harness is protected from the high engine temperatures. For high temperatures engine applications, nylon generally outperforms polypropylene, PP, due to its superior heat resistance and strength. While high-performance PP grades can withstand higher temperatures than standard PP, nylon's higher melting point and continuous use temperature make it more suitable for demanding engine environments. Polypropylene, which melts around 160 to 170 degrees Celsius, nylon typically has a more excellent melting point, about 220 to 260 degrees Celsius for nylon 66. PP's limitations, lower heat resistance. While high-performance PP grades can be used in higher temperatures, they generally have lower melting and heat deflection temperatures compared to nylon. Strength and durability. PP's strength and durability are lower than nylon's, making it less suitable for demanding engine applications. Other options. Consider braided sleeves, woven sheathing, or heat shrink tubing, depending on the specific needs. 3. Harness routing and placement. Avoiding sharp bends. Design routes to minimize sharp bends and kinks, which can damage wires and reduce their lifespan. Protecting vulnerable areas. Use protective channels in areas where wires are exposed to physical damage or environmental factors. Flexibility. Ensure the harness can flex and move without strain or damage. Strain relief. Use strain relief devices, like clamp or bushing, to prevent wires from being pulled or twisted excessively. 4. Design considerations. Cable management. Plan the routing and arrangement of wires within the channel to prevent overcrowding and potential damage. Shielding. For electromagnetic interference, EMI, concerns, use shielded conduit or shielded cable. Separation. Separate power and data cables to minimize interference. Accessibility. Ensure the harness is easily accessible for maintenance and repairs. 5. Testing and validation. Environmental testing. Subject the harness to relevant environmental conditions, temperature, vibration, etc., to verify its performance. Mechanical testing, assess the harness's resistance to physical stress and damage. Electrical testing, verify the integrity of the wiring and connections. 6 Standards and Regulations. IPCWHMAA 620, the industry standard for wire harness assembly and testing. UL, Underwriters Laboratories, standards, for specific applications, follow relevant UL standards for safety and compliance. Other standards, consider other applicable standards like IEC, International Electrotechnical Commission, or CE CENELEC, European Committee for Electrotechnical Standardization. By following these design guidelines, you can ensure the wiring harness's protective channels provide adequate protection and contribute to the overall reliability and durability of the system. Molded wire harness channels should be designed and manufactured to avoid sharp edges, sharp parting lines, and flash. Sharp edges can cut into wires, sharp parting lines can leave weak points, and flash can obstruct the channel or damage the wiring. Here's why and how to avoid these issues. Why avoid sharp edges, parting lines, and flash? Sharp edges. Sharp edges on the channel can physically damage the wires, insulation, and connectors, leading to short circuits, broken wires, or other electrical problems. Sharp parting lines. Sharp parting lines, where the two halves of the mold meet, can create weak points in the molded plastic. If the parting line is not properly sealed or the mold is worn, it can allow molten plastic to seep through during the molding process, creating flash and potentially weakening the channel. Flash. Flash is excess material that flows out of the mold between the parting lines or other areas. It can obstruct the channel, making it difficult to insert wires, or it can damage the wires or connectors. Ejector pin flash can damage wire harnesses. Ejector pins, used to eject molded parts from the mold, can sometimes leave small marks or dents on the part, and if the pins are not properly maintained or designed, they can cause flash or excess plastic to form around the pin area, potentially damaging wire harnesses. If the pins are loose, worn, or not properly aligned, they can cause flash, extra plastic that forms around the pin area. How to avoid these issues? Design. Rounded edges, design the channel with rounded edges to prevent sharp points that could cut wires. Proper parting line design, ensure that the parting line is designed to create a strong seal and prevent flash. A rounded mold parting line in injection molding can lead to higher costs and increased maintenance needs compared to a straight or beveled parting line. This is because rounded parting lines require tighter tolerances and more complex machining, potentially leading to higher mold costs and increased maintenance requirements. While a rounded parting line might be necessary for certain part geometries or features, it's important to carefully consider the associated costs and maintenance implications, as they are generally higher than those of straight or beveled parting lines. Avoid obstructions, ensure that the channel is designed so that there are no obstructions from flash or other defects that would interfere with the wires or connectors. Manufacturing requirements for molded wire harness channels. When you quote the project, consider the cost for precision molding, use high-quality molds and precision processes to minimize flash and ensure a tight seal at the parting line. Precision injection molding can be expensive due to factors like part complexity, tight tolerances, high-precision machinery, and the need for skilled labor. The more intricate the part and the tighter the required tolerances, the more complex and costly the mold will be. Additionally, specialized equipment and high-end machinery are required for precision molding, further increasing expenses. For applications with high liability, where even slight variations in dimensions or material properties and molding flash could lead to serious consequences, precision molding is a crucial option. It ensures the highest level of dimensional accuracy, consistency, and material integrity, minimizing the risk of failure or malfunction. For applications where high liability is a concern, precision molding offers a crucial advantage by ensuring dimensional accuracy, consistent material properties, reduced risk of defects, and increased reliability, ultimately leading to safer and more reliable products. Proper clamping pressure: use the correct clamping pressure to hold the mold together during injection to prevent flash. Material selection: select materials that are suitable for the application and that are less prone to creating flash. Post-molding. Deflashing: only if the customer approved the rework of parts in writing. If flash is unavoidable, use appropriate methods to remove the flash without damaging the channel or wires. Inspection: thoroughly inspect the channels for any defects before they are used. By paying attention to these details during design and manufacturing, you can ensure that molded wire harness channels are durable, reliable, and safe. Molded wire harness channels with living hinges made of nylon can break if the hinge is excessively stressed, if the material is too thin, or if the molding process is not optimal. Specific issues include inadequate cooling, slow filling during molding, or bending the hinge too quickly. Factors contributing to failure: wire harness channels with living hinges made of nylon. Stress: wire harness channels with living hinges made of nylon. Excessive bending or flexing can lead to material fatigue and eventual fracture. Nylon living hinges in wire harness channels can be prone to breaking if the material is too dry and brittle. This is because nylon, unlike polypropylene, can be susceptible to moisture absorption, which affects its flexibility and ability to withstand repeated flexing. While nylon can be a suitable material, especially in automotive applications, it's important to consider its limitations and choose alternatives like polypropylene, PP, or polyethylene, PE, for applications requiring high durability and fatigue resistance. Nylon's tendency to absorb moisture, it's hygroscopic, can cause issues with its dimensional stability and mechanical properties. To manage this, molded nylon parts are often conditioned with moisture by being placed in packaging containing water, or by other methods like steam, before or after molding. Water bath humidity: nylon parts are placed in a sealed bag with a saturated sponge or paper towel to allow them to absorb water gradually while stored or transported or waiting on the assembly line for assembly. Steam: parts can be steamed, but this method can be more rapid and may not be suitable for all nylon types. Benefits of moisture conditioning: reduced shrinkage: moisture conditioning can help to minimize shrinkage during cooling and storage, improving dimensional accuracy. Improved assembly: parts that have been moisture conditioned are less likely to have dimensional variations, making assembly easier. Plasticizer effect: water acts as a plasticizer, making the nylon more flexible and less likely to crack or break. If nylon is not properly dried before injection molding, it can become brittle and prone to breaking. Nylon is moisture sensitive, and excessive moisture can lead to hydrolytic degradation, reducing its strength and increasing brittleness. Once molded, nylon parts can be conditioned with a moist environment to help them regain some moisture and toughness, preventing brittleness. Proper packaging can help maintain the moisture content of molded nylon parts and prevent them from becoming too dry. Material thickness: wire harness channels with living hinges made of nylon. A hinge that is too thin may not have enough strength to withstand bending stress and may tear or break. Molding issues: wire harness channels with living hinges made of nylon. Inadequate cooling: insufficient cooling during molding can result in a weaker hinge with a higher risk of failure. Slow filling: slow filling during molding can create weak or uneven hinge areas. In living hinge design, the hinge is typically bent along the direction of material flow to maximize its strength and durability. This flow direction is crucial because it aligns the plastic molecules within the hinge, creating a stronger, more resilient structure. When molten plastic flows through the mold cavity, especially the narrow hinge area, the flow direction forces the plastic molecules to align themselves. For maximum strength, the molecules should be oriented perpendicular to the direction of bending, the hinge's flex direction. This is achieved by ensuring the flow direction is parallel to the hinge's length. A uniform flow rate across the hinge is also important to prevent weld lines or defects that could compromise the hinge's durability. Proper gate placement and flow control are critical to ensure that the material flows in the desired direction and creates the necessary molecular alignment in the living hinge. Hinge design. Short hinge length. A short hinge or a large distance from the hinge to the attachment point can concentrate stress and lead to failure. Hinge thickness. The hinge thickness should be carefully considered to ensure it is strong enough to withstand the intended stress without being too thick or stiff. Environmental factors. UV exposure. Prolonged UV exposure can degrade plastics and lead to fractures. Chemical exposure. If the part is exposed to chemicals, the selected material must be resistant to degradation. Nylon type. Some types of nylon may be too stiff and snap rather than bend when used in living hinges. Recommendations for preventing failure. Proper design. Ensure the hinge is designed with sufficient length and thickness, and consider the stress it will be subjected to. Optimal molding. Use a high velocity for filling and ensure proper cooling to prevent weak hinges. Material selection. Choose a suitable nylon material that is flexible and resistant to the intended stress. Avoid overflexing. Do not flex nylon hinges immediately after molding, as this can cause them to break. Consider environmental factors. Protect the part from UV and chemical exposure if necessary. For injection molded living hinges, polypropylene, PP, is generally considered the best material due to its balance of flexibility, fatigue resistance, and chemical resistance. Polyethylene, PE, is also a viable option, especially for larger, less complex designs. Polypropylene, PP. PP is highly flexible, resists fatigue well, and can return to its original shape after deformation, making it ideal for applications like flip-top bottles and lids. It also offers good chemical resistance and moisture resistance, enhancing its durability. Polyethylene, PE. PE is similar to PP but may be slightly more flexible and have lower friction, making it suitable for applications where the hinge needs to withstand gentler, slower flexing. Other considerations. While PP and PE are most common, other materials like nylon, ABS, and TPE, thermoplastic elastomers, may be used in specific applications where different properties are needed. For instance, TPEs offer added softness and grip. A significant disadvantage of using nylon for living hinges is its high moisture absorption, which can impact dimensional stability and structural integrity, especially in humid environments. Nylon's hygroscopic nature can cause warping and stress concentrations, potentially leading to cracking or breakage. Moisture absorption. Nylon is known for its high water absorption rate, which can lead to changes in its size and shape. This can be problematic for living hinges, as the dimensional changes can affect the hinge's ability to fold and unfold properly. Dimensional instability. The swelling and shrinking of nylon due to moisture absorption can create stress concentrations, particularly in the hinge area, which can lead to cracks and failures. Stress concentrations. Sharp corners or abrupt transitions in the hinge design can exacerbate the problem, as they concentrate stress in those areas. Trade-offs with impact resistance. Nylons that offer higher impact resistance are often more susceptible to moisture absorption, making it a trade-off to consider. Processing considerations. Proper drying and conditioning of nylon before and during molding are crucial to minimize the impact of moisture on the finished part. Material selection. While nylon offers advantages like flexibility and strength, materials like polypropylene, PP, or polyethylene, PE, might be better suited for applications requiring high durability and resistance to cracking under repeated flexing. Yes, nylon living hinges can become too brittle if they are over-dried during the molding process. Nylon is hygroscopic, meaning it absorbs moisture, and this moisture can have a plasticizing effect, making the material more flexible and impact resistant. Overdrying nylon can remove this moisture and lead to a decrease in flexibility and an increase in brittleness. Moisture and flexibility. Nylon's moisture content influences its properties. Moisture acts as a plasticizer, increasing flexibility and impact resistance. Overdrying and brittleness. Overdrying nylon removes this moisture, reducing flexibility and making it more prone to cracking or snapping, especially when subjected to stress, like in a living hinge. Drying process. During injection molding, nylon is typically dried to reduce moisture content to below 0.2%. However, overdrying can lead to issues with mold flow and can cause material degradation. Living hinge design. Living hinges, by design, are thin and subjected to bending stress. This makes them particularly vulnerable to brittleness if the nylon is overdried, potentially leading to premature failure. Importance of material specification. Material data sheets often provide specific drying recommendations for nylon grades, which should be followed to avoid overdrying. Degradation. If nylon is overheated or dried for too long, it can start to degrade, leading to discoloration and further compromising its properties. Nylon, being a hygroscopic material, readily absorbs moisture from the environment. Drying nylon before molding is crucial to prevent defects like splay or silver streaking on the surface, brittle parts, reduced strength, and dimensional instability. Why drying is important. Moisture as a plasticizer. Moisture acts as a plasticizer, reducing nylon's stiffness and strength while increasing elongation and toughness. Degradation of resin. Excessive moisture can degrade the resin, leading to shortened polymer chains and reduced strength. Appearance defects. Moisture can cause splay, cosmetic defect, or silver streaking on the surface of the molded part. Brittle or dimensionally unstable parts. Moisture can lead to brittle parts or those that are dimensionally unstable. Gassing. Moisture can lead to gassing during the molding process, causing defects like shorts, inadequate filling of details, or poor appearance, and bubbles, particularly in areas of thicker material, are often caused by trapped gases or air pockets, or by shrinkage during cooling. To address these issues, it's crucial to identify the type of bubble and adjust the molding process accordingly. Solutions to prevent bubbles. Improved venting. Ensure adequate venting in the mold, especially in thick sections and where flow fronts converge. Material drying. Properly dry the material to remove moisture. Adjusting molding parameters. Increase holding pressure, reduce injection speed, or increase back pressure to ensure the mold is fully packed. Optimize gate and runner design. Ensure gates are appropriately sized and located to facilitate proper flow and minimize air entrapment. Material selection. Choose materials with appropriate viscosity and melt temperature to improve flow and reduce shrinkage. Mold temperature. Adjust mold temperature, especially locally where voids tend to form. Drying process. Nylon resins should be dried to a moisture content of less than 0.2%. Drying can be done using desiccant dryers, which use compressed air and a desiccant material to remove moisture. It's important to maintain consistent resin moisture levels from run to run. After drying, it's best to process the resin quickly before it reabsorbs moisture. When molding materials with glass filling, do ensure uniform wall thickness, incorporate draft angles for easy mold release, and consider the abrasive nature of glass-filled materials on mold tooling. Don't design parts with very thin walls, create undercuts that hinder ejection, or expect highly polished surfaces with filled resins. Do's. Design for uniform wall thickness. Glass-filled materials are prone to warp, especially when walls are uneven. Uniform thickness helps maintain consistent cooling rates and reduces internal stresses. Incorporate draft angles. Draft angles facilitate the removal of the molded part from the mold and prevent drag or scrape lines. Consider abrasiveness. Glass-filled materials are more abrasive than unfilled plastics, so use hardened steel tooling and be mindful of wear and tear. Optimize parting lines and radii. Parting lines should be as inconspicuous as possible, and radii can improve material flow and reduce stress concentrations. Plan for internal support. Consider gussets, ribs, or other internal structures to support thin walls and prevent warping. Properly vent the mold. Ensure adequate venting to allow trapped air to escape during molding, especially with glass-filled materials. Select appropriate mold finishes. Filled resins may not achieve highly polished surfaces, so choose mold finishes accordingly. Don'ts. Avoid thin walls. Thin walls can lead to warping, especially with glass-filled materials. Design undercuts. Undercuts make it difficult to eject the part from the mold and can lead to damage. Expect highly polished surfaces. Filled resins generally don't achieve a highly polished look, so choose mold finishes that suit the material. Use materials incompatible with molded threads. Avoid glass-filled and high-temp materials for internal threads, as they can be difficult to handle. Neglect draft angles. Insufficient draft angles can lead to drag lines and difficulty ejecting the part. Overlook parting lines. Parting lines can be cosmetically undesirable, so design them carefully. Use excessive mold polish. The mold polish level chosen should be appropriate for the resin and the desired surface finish. When molding PA materials, do use proper drying techniques to remove moisture, optimize runner design, and consider part design for optimal mold filling. Don't ignore material flow analysis, rush the injection process, neglect mold maintenance, or overlook venting. Do's. Dry the material. PA is hygroscopic, meaning it absorbs moisture. Moisture can cause defects like silver streaks, bubbles, and reduced mechanical properties. Proper drying before molding is crucial. Optimize runner design. Runner shape should be rounded, and the injection port should be as short as possible. Avoid small gates for large parts, as they can cause excessive pressure and shrinkage. Consider part design. Pay attention to wall thickness, transitions between thick and thin areas, and draft angles to prevent defects like warp, curl, and sink marks. Use ribs and gussets. These features can help reinforce thin walls and improve structural integrity. Maintain mold temperature. The mold temperature should be within the recommended range for PA, typically 60 to 100 degrees Celsius. Use a dehumidifying dryer. This is recommended for PA and other hygroscopic materials like PBT polybutylene terephthalate, PET polyethylene terephthalate, PEI polyethyramide, and PSU polysulfide to ensure effective drying. Optimize gating system. Consider the gate size, location, and type for optimal material flow and to minimize stress on the part. Utilize hot runner systems. Hot runners can improve cycle time and material flow but require precise temperature control, adequate shot size and cycle time because hot runner systems in injection molding can contribute to the degradation of molten plastic. This is primarily due to the prolonged exposure of the plastic to high temperatures within the heated runners. Factors like excessive temperatures, long residence times, and improper venting can also accelerate this process. While hot runner systems offer numerous benefits, the potential for material degradation due to prolonged exposure to high temperatures must be carefully considered and mitigated through proper process control and material selection. In summary, designing and manufacturing wiring harness protective channels requires a meticulous approach, prioritizing safety and reliability through adherence to industry standards, careful material selection, and robust manufacturing processes. This ensures the integrity and performance of the harness, minimizing the risk of electrical failures and potential hazards.
面看见阿妹来，不高不矮是好身材，金银财宝我不要，只要你阿妹留下来。想你想你，真的好想你，一天想你一万回，每天想你走错了路，晚上想你睡不着，月亮圆圆天上挂，月亮里面有什么？月亮圆圆天上挂，月亮里面有我的阿妹。想你想你，真的好想你，一天想你一万回，白天想你走错了路，晚上想你睡不着，月亮圆圆天上挂，月亮里面有什么？月亮圆圆天上挂，月亮里面有我的阿妹，阿妹，我的阿妹。阿妹打秋千，秋千荡高起长春，好像胭脂云里传。阿哥阿妹在一起，阿哥阿妹在一起。阿哥阿